When I search for most litter items on Google, this is what I get. All the results are linked to cigarette butts. In this article from National Geographic, it says, what's the world's most littered plastic item? Cigarette butt. This one paper from Journal of Hazardous Material that says that 5.5 trillion cigarettes are being produced annually in the world, and the cigarette butt would reach up to 1.2 million tons and increase by 50% until 2025. This paper also mentioned that cigarette butts are the most littered items in Malaysia. In an investigation on the Malaysian coast, over 13,000 litter observed, and the most frequent of which was cigarette butt. This photo is taken from The Independent. You can see that the bird spotted feeding the chick cigarette butt, and this is quite devastating. Littered cigarette butts are the most widespread man-made pollutants. They can cause plastic pollution, they can harm plant growth, and also poison the animals that eat them. That brings to my topic today, cigarette filter waste as membrane fabrication material for oil and water emulsion separation. Kill 2 birds with 1 stone. Ladies and gentlemen, my name is Leong Chew Lee. This will be the content for my presentation today. Cigarette is composed of filter, tipping paper, cigarette paper, and tobacco. Cigarette filter or cigarette butt contains large amount of cellulose acetate. This cellulose acetate is very slow to degrade in the environment. A typical cigarette filter will take from 18 months to 10 years to decompose depending on the condition. On a different topic, oily wastewater is mostly produced from oil and gas industry. It poses a threat to the environment security as well as human health, as they may contain heavy metals, phenols, ammonia, and dissolved organic matters. So, purification of water from oily wastewater is vital in protecting the surrounding environment and saving water resources. Problem statement. In the previous study that was published in 2019 last year, nanofiber membrane was developed and utilized for separation of a less challenging feed of an oil and water mixture. Electrospun nanofiber membrane also has low mechanical strength, and they cannot be used as a standalone system without the additional support layer. Electrospinning process also takes a very long time to fabricate a single membrane sheet, and after a long run on the filtration, the membrane suffers from fouling and swelling effects. So our objective of this project is to fabricate and characterize a CA-based inverted membrane from cigarette filter waste and compare this membrane with established membrane, which is PVDF and PSF. We also want to evaluate the filtration performance of this membrane for oil in water emulsion filtration and compare the performance with PSF and PVDF membrane. Lastly, we also want to assess the membrane fouling propensity of these 3 membranes. Scope of study. So we want to develop a cellulose acetate membrane prepared from cigarette filter waste using phase inversion method with stainless steel mesh as the support layer. Then we want to analyze this developed membrane with established PVDF and PSF membrane. The filtration system that we are using is Crossflow Filtration in multiple stages using oil in water emulsion as the feed solution. These are the characterization tests that have been done on the CE membrane. So FTIR is to determine the chemical bonds of the CA membrane. Then contact angle goniometry is to analyze the hydrophilicity of the membrane. CFP is to determine the pore size distribution. EDS is to find the elemental composition contained in the membrane. SEM is to determine the microstructure, surface, and cross-section morphology. UV is to test the concentration level of the permeate. Literature review. These are some of the published papers on utilization of cigarette waste. This paper uses waste cigarette filter to develop nanofiber membrane. This paper, which was published in 2019 last year, is very similar to my project. The advantage of this nanofiber membrane that was developed from waste cigarette filter is that they possess super oleophilic and super hydrophobic, not to say they are also high absorption capacity with high porosity, high surface area, and high pore interconnectivity. But the limitation of this membrane is that they have weak mechanical strength. Also, the filtration system, which is gravity-driven process that they use, has no proven in industry scale. Electrospinning of membrane has yet to achieve industrial standard. So this is my project workflow. I first started with preparing the membrane of CA, PSF, and PVDF. Then I set up the filtration, which is using Crossflow Filtration with synthetic produced water as the feed solution. Then we use the membrane and test to analyze the performance, which is the flux and the permeability. Then we also identified the membrane fouling. We want to identify the total fouling, reversible, and irreversible fouling. Last one, we want to know the morphology of the membrane by undergoing SEM, CFP, EDX, goniometry, FTIR, and UV on the permeate. This is the preparation of CA membrane. First, I collected the cigarette filters. Then I physically cleaned the cigarette filters by removing tobacco, wrapping papers, and remove the burn tips. So you get the clean cigarette filters here. Then I clean the cigarette filters by putting them in the boiling water and stir them with several cleaning cycles. After that, I dry in an air circulating oven at 60 degrees Celsius overnight to remove any moisture content. Then lastly, dried cigarette filters were shredded into this form in order to stir better and mix well with the solvent. Next is the fabrication of membrane using phase inversion. So after I have added the solvent, it dissolved completely as I stir for 60 degrees Celsius for 24 hours. Then after the mixture has achieved the homogeneous phase, then I pour onto this plate. So this is the stainless steel mesh with the size of 400. So I pour onto this and I move over to form the thin film. So this thin film will be immersed in the water bath to solidify them. So this is where the phase inversion process happens. So after some time, this has been solidified. This is the custard membrane, and we use this part to analyze the performance of the membrane. This is the membrane fabrication parameters. For CA membrane, we undergo phase inversion method. We use 10 weight % of clean cigarette filter waste, and we mix with 90 weight % of DMF, which is the organic solvent, and cast it on the stainless steel mesh with a mesh size of 400. And that subsequently for PSF and PVDF with different membrane parameters. This is the feed preparation. So this is the parameter in order to prepare the synthetic produced water. Crossflow filtration. So we will be testing our membrane in this filtration cell. I will play a video here. This is a peristaltic pump which is over here. And then it supplies the pressure to this, and this is the filtration cell where the membrane is inside, and this is the collected permeate where we measure with the measuring cylinder. We measure the volume. Then this is the produced water emulsion tank. So the transmembrane pressure is 0.2 bar and the volumetric flow rate to move the fluid in it is 13.4. So the fluid runs on full recycle system. So this is the formula to calculate filtration flux, membrane permeability, and rejection. In order to perform membrane fouling analysis, we run the filtration on the clean water to obtain the clean water permeability for 60 minutes. After that, we perform filtration of produced water and conducted for 5 cycles where Each cycle is 50 minutes of produced water filtration followed by 5 minutes of membrane washing with tap water. This is the formula to calculate total fouling, reversible fouling, and irreversible fouling. Result and discussion. So this slide shows the SEM images where ABC is the top layer or surface of the SEM images, DEF is the cross-section SEM images, where AD is the CA membrane, BE is the PSF membrane, and CF is the PVDF membrane. For the top layer, for the surface SEM images membrane, you can see that all samples have the visible surface pore distributed evenly and within microfiltration range. CA over here has the good surface property like the one prepared from PSF and PVDF. So the microstructure surface suggests that CA has the potential to be used in oil-water emulsion separation. And for the cross-section over here, we can see that all three membranes show an equally asymmetrical morphology, which is a common structure of membrane prepared from non-solvent phase separation. Next result shows the membrane pore size and distribution. So this is the result that we obtain using capillary flow porometer tests. We can see that over here that CA, which is denoted by the blue line, has the highest pore size diameter of about 0.1 micrometer. Membrane works based on the size exclusion theory that says that the smaller pore size is better in order to reject large particles. So a typical size of an oil droplet in emulsion are in the range of 0.1 to 10 micrometer. So theoretically, CA has the ability to remove emulsion droplets. So we also compare the CA that we developed with commercial CA, and it is found that the one that we developed has 4.7 times smaller pore size diameter than the commercial CA. This proves that the prepared CA membrane from cigarette waste is as compatible as the commercial membrane. Next, we move on to surface contact angle. Surface contact angle is tested using goniometer, and surface contact angle that we tested is static contact angle, which tells us the permeability and fouling properties of a membrane. A membrane is considered hydrophilic when the contact angles falls between 0 to 90 degrees, and hydrophilic membranes are ideal in oil and water emulsion treatment since they are able to attract more water and prevents contaminants molecule from moving across the membrane. Based on this figure over here, we can see that CA membrane from cigarette filter waste has the hydrophilicity properties with a contact angle of 74.1, which is way better than PVDF, which show hydrophobicity properties. Next result show the FTIR. FTIR is to analyze the chemical bonds of the membrane. This FTIR is run on CA membrane to test that if this membrane is really cellulose acetate membrane. The peaks at the CA membrane correspond at 1747, 1230, and 1050 correspond to carbonyl stretching, carbonyl symmetric, and asymmetric stretching vibration of COC, which is ether. And this similar findings was also reported on nanofiber membrane that was published in 2019. They also use cigarette filter waste. So similar findings also reported from this article. Next result shows the EDS result. So EDS tells us the elemental composition. And from this table, EDS mapping tells us that the CA has the highest oxygen composition, which indicates the presence of hydrophilic functional groups. This justified that CA has higher hydrophilicity properties than PSF and PVDF. The presence of carbon and oxygen is also supported by the FTIR analysis earlier. Moving on to clean water permeability or CWP. So clean water permeability involves the passage of water molecule across the membrane under crossflow filtration. So from this figure, we can see that the CA membrane has way significantly high permeability than PSF and PVDF. From the SEM top layer images also suggest that CA have large visible pore size and higher distribution. This means that more water molecules flow through CA membrane, which increases the water flux and therefore explain the high permeability of CA membrane. Moving on to filtration performance. You can see from the figure that CA membrane has the highest permeability for the first 50 minutes filtration, and it is maintained until the end of the filtration cycle. This could be the high oxygen content in the membrane, which enhance the surface hydrophilicity, which is beneficial in repelling deposited oil droplets when treating oil and water emulsion. CA membrane also has high surface porosity, which enhance more water to flow across the membrane. Over here is the clean water flushing, which helps to remove oily foulants and reduce fouling effect on the membrane. So you can see that over here, after the clean water flushing happens, this permeability will increase the next cycle, and over here it increases the next cycle, next permeability. This one will also increase the permeability of the next cycle. Next is the membrane fouling analysis. As the filtration cycle increases, the total fouling, which is denoted by irreversible and reversible fouling, also increase. For PVDF, which is over here, PVDF shows that the total fouling at each cycle is relatively lower than PSF and CA membrane, which means PVDF have lower degree of permeance loss and better anti-fouling properties. CA, on the other hand, suffers a high degree of irreversible fouling, which is denoted by the red line here. Since the first cycle, since CA have a 5 times higher clean water permeability than PSF and PVDF at the initial cycle, which was shown earlier, we believe that high fouling rate of CA was caused by rapid compaction, which result in a lower permeability. So that brings to the conclusion. The column over here is the objective, and this is the conclusion. We can conclude that the CA-based membrane was successfully fabricated using phase inversion method. So the CA also has hydrophilicity properties, which is lower than established PVDF and PSF membrane. So this is a suitable membrane to be used in oil in water emulsion. CA also show a promising initial flux of 452 for filtration of oil in water emulsion, but the flux dropped gradually after a long filtration run because of membrane fouling and swelling. CA also outperformed in terms of filtration performance by having the highest permeability compared to PSF and PVDF. In terms of membrane fouling propensity, it suffers a relatively high irreversible fouling, and these are some recommendations for this project. Addition of additive agents, tannic acid, PVP, will help to improve the hydrophilicity and wettability of the membrane. Second recommendation is the optimization of membrane fabrication parameters like polymer concentration. Maybe you can try with different solvent, with additive system, or maybe with other phase inversion parameters which can optimize the membrane fabrication. And that's all from me. Thank you very much for listening. See you on 7th September.